So, good morning. Thank you so much for joining us this morning. And I'm pleased to introduce this webinar that is dedicated to the importance of federated learning in the medical research and in particular for neurodegenerative diseases. It's a webinar co-organized by 3 EU-funded projects, LETHE, BRAINTEASER, and HEREDITARY. I am Natalia Allegretti, and I'm a senior innovation manager at the European Connected Health Alliance, and I'm the dissemination and communication leader of one of the 3 projects, in particular, BRAINTEASER, as you can see. Before we kickstart with this morning activities, let me share with you some points in relation to housekeeping. So the webinar is recorded, and soon after the event, the recording will be uploaded on the 3 projects website. During the presentation, please be so kind to turn off your camera and mute your microphone. Questions and comments can be posted in the chat function, and we will address them during the Q&A session. And also be aware that subtitles are available. To activate them, you should click on the More button, go to the Language and Speech function, and you will find an option to turn on automatically generated subtitle. The agenda for this morning foresees a first part dedicated to presentations from our panelists, while then we would like to hear from you. So the last part of the meeting will be dedicated to questions from the audience and comments from you. And now let me introduce our speakers today. So we have Hannes Hildenberg. He is a researcher at the Institute of E-Health at the FH Joanneum, and is a doctoral student at the Medical University of Graz. And then we have with us Umberto Manera, who is a neurologist and assistant professor at the Rita Levi-Montalcini Department of Neuroscience at the University of Torino. And now I think that without further ado, we can start this morning working session with the presentation from our panelists. And in particular, let's start with Hannes and the LETHE Project. So Hannes, the floor is yours.
Thank you very much, Natalia. Hello everyone. My name is Hannes Hilberger, and I'm a researcher at the Institute of eHealth at the University of Applied Sciences in Graz in Austria, as well as a doctoral student at the Medical University of Graz. And today I'm honored to give you a short introduction to federated learning and how I want to apply federated learning within the LETHE project as part of my dissertation. So before I want to give you an introduction to federated learning, I want to give you some motivation why this approach even exists. So as we all have smartphones and wearables, we collect many data, but also in organizations like hospitals, for example, they have many data which is not used yet. So about 0.01% of the data is only used to train AI models. That means we have a lot of unused data silos in many sectors, as well as the unused data on our mobile phones. And to train models on this data is really difficult because of the data protection regulations like the GDPR in Europe, and therefore the transport of the data and the acquisition of the data is really difficult. And if one organization tries to train an AI model, there could be the case that there is not a great generalization across the several institutes. Meaning, and that reference I linked here, Xu et al. Tried to predict COVID-19 for different patients, and they reached 97% sensitivity of the predictions in the Donghi hospital. But when they tried to the model out in another hospital, in the Wuhan hospital, only 72% of sensitivity was reached. And the last point why federated learning was introduced is that researchers and small institutions cannot benefit from the vast amount of data that exists because they do not have the resources, or they have to agree to complex data processor and data controller agreements. So now with that motivation behind, we can talk about federated learning. So how does the traditional machine learning approach looks like? So we have a central server and we collect data from different devices and clients. So for example, we have data on our mobile phones, on smartwatches, or some clinical data, for example, and we collect them all in one place in a database, like in the yellow box. And with that data, we can train neural networks or regression models. So now what does federated learning make differentiate is different to traditional machine learning approaches. So instead of bringing the data in one central place, the data sits on the client devices. So we move the training model to the data instead of bringing the data to the model. So we differentiate between two different approaches. The first one is cross-device federated learning and was the initial idea by McMahon in 2016, where the models are trained on mobile phones or IoT devices. And in new iterations, there is also the approach of cross-silo federated learning. Here we have a lot of databases which are very big with over millions of records. And one practical example for federated learning, which many are not aware of, is the Google keyboard, which is trained by federated learning. So that mechanism which completes your sentences or give you suggestions for the next word. So now with that idea in mind, it is really abstract that we move the model to the data. What does this exactly mean? So here I want to present you a high-level overview of that mechanism. So on the bottom, we have the so-called client devices, which could be thousands of mobile phones where we want to train a model. And then at the top, we have a server, a central server that coordinates the training. The server has a so-called global model, which is defined on the server side, and the parameters of the global model are sent to the clients. The clients, so the mobile phones in that example, train their model locally with their own data. So that means the data does not be sent to the server, but the so-called model updates are then sent back to the server, but no raw data is exchanged. In the final step, the server aggregates all those updates and a new global model is created. And those 4 steps can be repeated as often as desired. So for example, for over 50 training rounds or 100 training rounds. So now that we know how federated learning works, we can have a look on the data distribution of the different clients. So we differentiate between horizontal federated learning and vertical federated learning. And as we can see here in this image, we have 2 different clients, which are hospitals. Those 2 clients share the same set of features, meaning age, weight, height, sex, and diagnosis. And we want to predict the survival rate of one individual, so our label. But the 2 clients differ in their samples. So those 2 clients have different patients in each hospital. The other big type of federated learning is the so-called vertical federated learning. Here we can see again that we have 2 clients. So one client is a hospital and the other client is a blood bank. Those 2 types now share the same type of patients, but do not share the same type of features. meaning that we have different features for the blood bank than the hospital, which is obvious. But the prediction of the survival rate is still the same as in horizontal federated learning. So here the challenge is for vertical federated learning that you match those two participants, that it really is the same patient with the different features of the client. So this is a quick overview of federated learning, but let's look at the benefits and the challenges of this approach. So since the data remains at the clients, so mobile phones or hospitals, there is no exchange of the real data, and those data cannot be leaked. And we also do not have to exchange all those big data. If you think of medical imaging, where the data size is really, really big. With federated learning, we can also enable collaboration across data silos, as I've shown you on the previous slide with the vertical federated learning. We can also achieve a better personalization. For example, for the Google keyboard, that you have a few layers with your personalized model. And on the top, we have some layers of the neural network, which is exchanged with the server back and forth, so that you still got the advantage of the whole global model, but also some kind of personalization for your words, for example. But there exists also a few challenges which we have to deal with federated learning. So the first one is heterogeneous data, meaning that, for example, one client have much more data than the other one, and that is called quantity skew. Other skews that happen are attribute skew, for example, that not all the clients share the same features, or that the data collection or the gathering of different features is different from the clients. But also the case could exist for the labels, that some clients have all label types, but some have not, which I come later back in the LETHE example. Another problem or challenge we have with federated learning is the communication overhead. So if we think about 1,000s or thousands of mobile devices that train the models, and we have over 50 or 100 training rounds, each time the server and the clients exchange the model parameters, and therefore a lot of communication between those devices occur. Another challenge is the client reliability. So for example, if one smartphone turns the internet connection off, the device cannot be part of the training anymore. But also what can occur is that they have different hardware, and one device or does the training faster than other devices. And then there's the case, should we wait for all devices to finish, or do we only select a portion of the device that trains nearly with different speed? And the last point, the privacy risks are a bit contrary to the benefits, but attackers will try to generate or regenerate the data that was used for model training by so-called model inversion attacks or membership inference attacks. And yeah, that would be a bit too complicated to go into detail now. But now with that foundation of federated learning, I can talk about the LETHE example and what I try to train, or what models I try to train in the LETHE setting. So before that, I have to give you a quick introduction to the LETHE project. So around 45% of dementia cases are attributed to 14 modifiable risk factors, as you can see here on the right in the Lancet publication. And with those facts in mind, the members of the LETHE project also took inspiration from past studies, like the finger study, a randomized control trial conducted in Finland that demonstrated a positive impact on cognition by targeting various lifestyle domains. And we in LETHE also have a 2-year-long trial, so such as finger, with 160 study participants in 4 clinical centers, but we have ICT support, which I will show you later on. And one special feature of LETHE is that we have the 4 clinical centers in 4 different countries. So namely in Austria, in Finland, in Sweden, and in Italy. So in LETHE, we have 2 different phases of data collection. So the first one is that we gathered data sets from all of those clinical centers. And that looks like the following. So we have the finger data set from a randomized control trial, as well as 3 different data sets from the different memory clinics. And what I want to do here is to predict the cognitive status, meaning if the patient has the status cognitive normal, subjective cognitive impairment, mild cognitive impairment, or dementia. And the data sets, so the clients, are then stratified by the cohort. So the finger data set is one client, the Regal data set is one client, the GDOC data set is one client, and the RDA data set is one client. And I've talked with the challenges about heterogeneous data. And what we can see here is that the label distribution is very, very off for each data set. So since the finger data set is a randomized controlled trial targeting cognitive normal people at risk, we can see that we have only the class cognitive normal for this data set. For the Hattinger data set, we only have SCI and MCI. And for the Solna and RDA dataset, we have only a small portion of cognitive normal patients. So this is one of the main challenges with federated learning on how to deal with such a distribution of the labeling. And here, such label awareness approaches exist, which I will try out in order to get a model that can predict the cognitive status. So the phase 2 of LETHE is about the prospective study, which we are currently performing now. And here we have different devices or where we want to collect the data. So we have on the one hand, Fitbit data that collects sleep, activity, steps, and so on. Then we have the LETHE app. So where we collect, for example, cardiovascular risk factor data as blood pressure or alcohol and smoking intake. Then we have the clinical trial management system, where we collect all the clinical relevant data. The CCOG is a cognitive test that is performed every 6 months. And we have the C-Train data, where the study participants can play cognitive training games. And we already published a paper on how the approach looks like and how I want to train the AI models with federated learning for each of those data sets we are currently gathering now. And yeah, as you can see here, this is nearly the same high-level overview I showed you in the beginning, but it is more advanced since we also apply some security mechanism like differential privacy. So this was a short overview of how federated learning works, but also how I want to apply federated learning within the LETHE project for the retrospective and the prospective data in the 2 phases. So thank you very much for your attention, and I'm happy to answer all your questions afterwards in the discussion round.
So, Hannes, thank you so much for this very interesting presentation. Questions are coming, so you will address them during the Q&A session. And now I would like to leave the floor to Umberto, who will talk about federated learning again and the implication within the BRAINTEASER and the HEREDITARY project. Umberto.
Thank you very much, Natalia. Good morning to everyone. I'm Umberto Manera. I'm a neurologist, and I'm very honored to share with you this morning the insight of our recent efforts to try to bridge two different European projects, the HEREDITARY Project and the BRAINTEASER Project. Today I will focus my presentation on the techniques, on how the novel techniques of federated learning developed in the HEREDITARY Project can significantly advance the AI models that we created in another previous project that is BRAINTEASER. And I will focus on the main topic of the BRAINTEASER project, which is ALS patient and MS patients. So let's start from BRAINTEASER. BRAINTEASER it's an European Union-funded project that involves 11 partners and is run by these two fantastic researchers, Professor Maria Fernanda Cabrera from CERMAS Madrid and Professor Barbara Di Camillo from the University of Padua, so Spain and Italy. The BRAINTEASER was focused on the use of artificial intelligence, as I say, to improve care for ALS patient and MS patient. If you are interested more on BRAINTEASER project, you can scan the QR code at the end of this slide. Trying to make the complex structure of BRAINTEASER a little bit simple, we can start from the data. We basically started from collecting data from many different sources, from apps, from portable sensor, but also from clinical documentation and also from the environment. So these were the three main domains of data collection. We use this data to train AI models that can be able to classify different patient, one patient to another, according to different phenotypes. We also try to use this differentiation in phenotypes to predict progression. So we simulate different kind of we prepare different kind of models. And the last objective of the project was to give feedback directly to clinician, to healthcare professionals, so clinician, nurses, but also have the possibility to give some feedbacks also directly to patient through a web app that and a mobile app that we developed during the project. As you can see, the data collection of the BRAINTEASER project happened in 4 different clinical centers from 3 different countries, so Madrid, Spain, Turin, and Pavia in Italy, and Lisbon in Portugal. This is what we call the data ecosystem of BRAINTEASER, because the project has collected both retrospective and prospective data. The retrospective data came from ALS and MS registry, but during the project, as Hennes, for example, mentioned before, we have some troubles at the very beginning of the project because we also started the project during the COVID pandemics, but we were able finally to recruit during the project more than 100 people with ALS and 200 people with MS. We give to this patient, to the prospective cohort of BRAINTEASER, 2 different kind of device, a smartwatch and an air pollution detector, as you can see from the slide, which is the Atmo2, which is the device in the extreme right. This is a portable device, let me explain briefly, that is able to detect several air pollutants, for example, PM1, PM2.5, PM10, but also volatile organic compounds, humidity, temperature, so a lot of features that surround the patient. For the environmental data, we also try to collect data not only from this kind of sensor, but also using data from different European environmental agencies. Using both for the retrospective part of the project, we use both population-based, but also clinical center database. We were able to collect about 2,200 data from 2,200 people with ALS and 1,800 more or less people with MS. And we were able to include in this data set static clinical variables for ALS, the ALSFRS score, which is the most important functional rating scale for ALS, respiratory data, so spirometry data, for MS, and for all the ALS cohort, also environmental data connected to these patients. For MS, we were able, for the full cohort, to collect static variables, data, also ADSS score, which is the most important functional rating scale for MS, the number of relapses. As you know, MS is a disease that is characterized from some periodic worsening of the symptoms. And also in a subgroup of patients with MS, we were also able to connect environmental data. During this phase, we have to face many challenges because we were very interested in the initial part of the project on data protection, because when the project started, federated learning was not so diffuse. So we used traditional way to cope with data protection and privacy. We also have to face some troubles with data quality and completeness. We also have to check for interoperability, because we started from a data set that were originally built in different languages, for example, in Italian, in Portuguese, and in Spanish. So we have to try to merge this kind of data, and also we have to define, and we try to define from the very beginning of the study also data governance of this kind of data, because we want to be sure, want to ensure the continuity of access to this data over time, also when the BRAINTEASER project is going to finish. As a consortium, but as I show in this slide, especially with the contribution of University of Padova and BELIT, we developed specific ontologies tailored to MS and ALS to try to harmonize terminology across languages, but also across different centers and different systems. And in order to be compliant with the GDPR, we emphasize in the informed consent that no commercial exploitation of the data would have been conducted, but we train and we derive some models from this data, and because we have a specific exploitation plan in the project, we state that only possible exploitation, commercial exploitation of the AI models derived can be done. During the project, we also organized 3 international challenges during the CLF conferences. And if you are interested, to take a look to both BRAINTEASER data and BRAINTEASER ontology, you can use these 2 QR code that directly link to the Zenodo platform. Considering that the project, BRAINTEASER project, is finishing now, because we are finishing the project in June. We started at the very beginning, during the BRAINTEASER project, we published an initial paper based on a systematic review of all AI-based models existing in literature on ALS, and we are finalizing also another review on AI models in MS. And throughout the project, we developed over 20 different predictive and stratification AI models, and we test this kind of models, and we decide to deploy 6 of this model also in the clinical dashboard that we developed during the project. So now there is a possibility for clinicians to include, for example, new patient in this platform, and to run this kind of model And especially we focus on models on ALS, and they are models that can, for example, predict survival. They can predict the need for ventilation, the need of placement of gastrostomy for enteral nutrition. Now we recently deployed the final version of the app and the clinical tour, and we we are finalizing now the exploitation plan and also the roadmap for the certification of these tools and models as software as a medical device. So moving from BRAINTEASER to HEREDITARY. HEREDITARY is another funded project that I'm very lucky to be part of. The project is aided again by University of Padua. Gian Maria Silvello is the project coordinator. Now is the project coordinator of 18 partners, so is a very big project. HEREDITARY is basically about building an interoperable, secure and privacy-preserving infrastructure to integrate multimodal health data. So it is a project on federated learning, as Hannes explained in the previous presentation. What we are dealing with now is basically genetic data, imaging data, biosignal data, also environmental data, and of course, clinical data, so data that come from clinical visit. We are also interested in data that come from literature, for example, scientific literature, and also from society. Our focus is the gut-brain axis and also neurodegenerative disease. I will try now to explain the structure of hereditary, but hereditary is, as you can see, for example, in the figure in the slide, is basically built on 5 interconnected layers. So if you follow me through the figures, you can see that the basic layer is the federated network infrastructure. This is the real engine of the project, and this layer is the one that enables us to perform machine learning across multiple institutions without moving raw data, as Hannes explained before. The lower layer is the layer of the data. So this is basically formed by the 5 clinical use cases that I will explain you later, and also the possibility to include data from open source data, so open data. We focus in this layer on collecting and also pre-processing high quality data from clinical, genomic, and different environmental sources. Then if we move up, you can see the layer of the multimodal semantic integration platform. In this layer, we are trying to harmonize in an ontology-based way all the data and use a quite sophisticated polystore system to merge all the data that you can see can be different, can be derived from different sources, and this is basically the multimodal semantic platform. Then we have the multimodal analytics and learning platform, which is the layer able to extract different patterns to try to manage the variability of the data, missing data, complexity of the data that we are collecting. And then at the very top of the project, we have the visual analytics and interaction layer. And this is the layer where the data become truly accessible because we are deploying now interactive dashboards and also some exploratory tool to interrogate and to interact with the data of all the hidden layer. To summarize a little bit, Hereditary is basically a project about multimodality because we include genomic, imaging, text. It's about data integration because we plan different scenarios, starting from a simple scenario to much more complex scenarios. is about multilinguality, because not only we have to cope with different languages, but also we have to try to merge the languages of clinicians, of patients, of society, in order to be in line with the same information. And it's also about privacy and security, because just to repeat, we manage very sensible data, speaking about health data. So in hereditary, we do not have only 2 diseases, but we planned these different 5 use cases characterized by an increasing level of difficulty. And we focus, as you can see, for example, in the first 3 use cases on neurodegenerative disease, so ALS, Parkinson's disease, dementia, and also MS, and also in the gut-brain interaction in the last 2 use cases. And in this initial part of the project, we are now focusing on use case 1 and use case 2. So we started with use case 1 with a single neurodegenerative disease, basically ALS, in a single center, basically data that come from University of Turin, but using an integration of multimodal data, starting to perform supervised learning and cluster analytics in a subgroup of patients, trying to classify patients in different clusters linked to specific genetic variants or linked to specific clinical phenotypes. And then we are now moving to use case 2 by including also other neurodegenerative disease, neurological disease, and merging data with the same ontology, but that come from different centers. And we are now making the federated experiments in these latest weeks. So we can focus on the bridge now, and hereditary is a project that brings powerful federated learning methods that allow AI model training across multiple sites, preserving data privacy, so make much more simple for a project, for example, as a BRAINTEASER, to make analytics, train models in a secure way, but it's able to empower also the BRAINTEASER project. This is very crucial for BRAINTEASER because we don't need to centralize data using federated learning techniques due to ethical and legal constraints. And as you can see from this slide, I try to list all the benefits, but probably there are more benefits to cooperation between these 2 projects. We share, first of all, expertise, knowledge, because one of the BRAINTEASER is a project that is finishing, and hereditary is a project that is ongoing. We can compare also federated and non-federated analytic results, because we already performed some analytics AI models using non-federated techniques, and now we are replicating this kind of analysis using the federated learning platform, and it's working. And then, for example, we also share, and we can reuse also the ontology that we built during the BRAINTEASER project. Also in this project, we can enrich dataset, we can improve the performance of AI model with new data, and we can make also joint experiments, and also in a collaborative way, we can have a higher impact also by publishing, for example, collaborative papers, scientific papers. So we started, I will speak just very few minutes on giving 3 examples. We started now sharing, for example, the ALS and MS dataset developed in the BRAINTEASER project, also with the hereditary consortium. And now we are trying to retrain and validate some models using this federated learning infrastructure. So under privacy constraints and comparing the data, as I said before, and the results and the performance index using federated analytics versus the standard analytics. We also reuse, we are now reusing and also expanding some of the ontologies from the BRAINTEASER to ensure what is called semantic alignment with other available, for example, open access dataset. And now we are enriching the dataset with complementary data types, for example, genomic data and also imaging data. And we are trying also to include data that come from, for example, from microbiome and gut-brain interaction, which are the core of the hereditary project. And we also empower new collaboration because by building this secure but accessible federated learning infrastructure, we can think that, for example, we can try to train and validate the BRAINTEASER project on new patient cohorts. We are now trying using data that are not from new clinical centers, but we are planning to do so. And now we are, for example, using open data. For example, we recently included the open Answer ALS dataset into the hereditary infrastructure to try to make some kind of new analysis. So to conclude, I think that the collaboration between hereditary and BRAINTEASER can be considered as a sort of a paradigm shift on medical AI research because we are going practically toward a federated, privacy-preserving, and semantically interoperable system. These are probably the future of research in health. And by linking this project, we can also try to create a sort of sustainable frameworks for data governance and also to improve the international cooperation. So I will thank you for, I'm thanking you for your attention. I look forward for your question. Thank you very much.
Thank you. Thank you, Umberto. So I think that we are now ready for the Q&A sessions. We have questions for both of you. So I might start with the first presentation, so the one from Hannes. The first question that we have received is to analyze data from different sources by federated learning. Is it needed that the data are first converted in a common data model? And if so, which common data model do you advise to have optimal analysis?
Okay, yeah, thanks for the question. So what we did in LETHE when we gathered the retrospective data from the different clinical centers, we sit together and made a structured data repository. So meaning that we developed a guideline on how the data looks like. So we have the data fields, X description, how can it be recoded so that it is all in the same structure and also that all have the same labels. So we have created our own structured data repository, but we can also think about to put it in some common data model like in OMOP, for example, or that we generate FHIR resources for all the data, which we also have mapped already, but didn't have bring it into the form that everything is in FHIR format. So here we also had a deliverable, which is publicly available, where we can see how all the data we've used in LETHE is mapped into the FHIR standard. I hope that answers the question.
If not, dear audience, please feel free to ask additional questions, obviously in the chat box. And Umberto, maybe one for you. What kind of criteria for data quality are you enforced across all these data inputs that you have presented?
What we use for data quality, but practically, I know if the answer is mainly related to BRAINTEASER, but we practically create and co-create with the engineer this kind of ontology, and we make we share different data set. We convert this data in an ontology-based data set practically, and then we reversely checked all the ontology that our colleague from the engineer department makes in order to be sure that everything was mapped in a correct way. If I can answer correctly to this question, this is what we've done.
Thank you, Umberto. Hannes, how do you deal with the labeling noise?
Yeah, so I've presented the 4 steps for the model training. So there exists different mechanism that aggregates the server updates. So there are so-called averaging mechanisms, and there are some few that already deal with aggregating such data. So there's, for example, the FedProx averaging algorithm, as well as the FedCore algorithm. So the FedCore is a multi-step approach where in the first step, noisy clients, so to say, are identified and that they can remove this data which is too noisy. So there is the noisy data and the so-called cleaned data, and they try to reduce the noise data that it doesn't impact that hard for the training. So these are the approaches I will also try. There's also some papers about the label awareness, which introduces some balance factors for the heterogeneous data I presented before. And yeah, that are the approaches I will follow. And yeah, there's much literature about on how to deal with such situations.
Thank you, Hannes. And Umberto, we have another one for you. What federated learning platforms / frameworks did you use?
Yes, I must remind to the audience that I'm a neurologist, but I know that we use the Docker for make the infrastructure, and also we are now using the Flower platform. So I'm not able to get into details because it's not I mainly based on data cleaning, data collection, data interpretation, and not directly in the use of the platform. But I'm learning now.
You are learning now.
Thank you.
Maybe.
Yeah, a little bit. It's quite complex. Maybe Hannes is.
Hannes, please.
Sure. So I've used several frameworks. So in the past, so when I began with dealing with federated learning, I used a PySift framework, which is from OpenMind. And then in the paper I presented, I also created own framework, also for one thing that I deepened my understanding of how federated learning works, and that I wanted to make some enhancements which are very important for me. So as not only the model parameters are exchanged, but also the model itself. So the whole model architecture is exchanged. So that was one crucial thing for me. But if you really want to begin with federated learning, I would also recommend the Flower framework right now. So the Flower framework is open source. They have very good documentations and blogs on how to use various architectures. And I also did this every year with some students, and they were also happy about it. And it works really well with different kinds of data. So you have examples for imaging data, but also tabular data, or I think even now for large language models as well. So if you want to begin with it, just explore the Flower framework and the documentation, then you're good to go.
Yeah, this is why we decided Flower. Yeah, because now we are using just data, not imaging data, but we know that this is an infrastructure that can also merge genetic and imaging and multimodal data. So yeah, thank you for for your help.
And Umberto, maybe this one can be really for you. We know that BRAINTEASER has been really a participative project within all the stakeholders involved in this long journey that we went through, and the patients played really a relevant role. So how are patients involved in guiding the BRAINTEASER project, but also the HEREDITARY project?
Yeah, but in both projects in two different ways. But for example, in BRAINTEASER project, we use different kinds of solutions to try to involve patients into the project. We basically built a community of practice, so an infrastructure that we're able to connect not only patients but also, for example, healthcare professional and share information about these two diseases, so ALS and MS. Then practically we co-designed the web tool and the app tool with patient, because we started to recruit patients in the initial phase of this project. Is not directly part of this conversation that we have today, but we practically co-designed the app and we fixed all the small errors. And also another very nice thing that we have done, for example, for ALS, we also involve patient association, and practically all the advice that clinician give to patient were also validated and built by involving especially the Portuguese Association for ALS patients, so the APELA. In HEREDITARY is quite nice because we are making labs, because HEREDITARY is basically a project on share, and also there is a specific work package on try to understand also the differences in language and concept, because especially in healthcare, different words can mean different things. If you're a patient, you're a doctor, you're a social worker, so it's very difficult to create ontology based on this different language, and also to retranslate back when you get some results to the specific audience. So we are performing now, I think, the 3 social lab and health social lab have been performed. We have one in Turin, one in Padova, and I don't remember where is the next one. I'm sorry, but it's a complex project. And so it's nice. There is one of our partners, which is Observer, which is running this kind of experiment. So it's quite good to have it.
Thank you. And we are running short in time, but Hannes, we have another quite complex question for you, which is coming from CERT. So what about the validation of the models? How do you ensure that validation is both effective and free from bias? What strategies do you use to avoid issues like data imbalance or non-representative client sampling, missing data?
So yeah, I think there are different cases. So how I am doing it in LETHE and how it could be done in general. So in LETHE, I create a train, validation, and test data set, but for each cohort. And the test data set will be then on the server side, where we validate how good performs the model for all the cases. And yeah, the test data is never used for training. It is just for the validation of the model in the end. And or for each training step, you can also say the training and the validation data stays at each time, so at the clinical centers. So one other idea of federated learning is if you have multiple cross-silo or cross-device federated learning, you can also think that you use some clients, not even for training, but for the validation of your model. So for example, small institutions which have not so much data, you could possibly use them for the validation. So you train models on, for example, 5 clients and use the 6th client for the evaluation of the model. How does the model perform there, for example? So these are the 2 approaches. I follow now the approach because I do not have that much external validation data that I created test set before. But in reality, you can use other devices, for example, for the evaluation of the model, how good it performs.
Thank you. So if no further questions are there, let me really thank everybody for being with us today. Let me share with you that we had a peak of 60 participants at this session this morning, so I think it's a great success. There is a huge interest, clearly, around this topic. My wishful thinking is that LETHE and BRAINTEASER that are coming to an end really can leave a legacy and build, let's say, the ground for further research in this very important area related to neurodegenerative diseases. Let me thank my speakers, so Hannes and Umberto, thank you so much for being with us today. And let me thank the Lisbon Council, in particular, John Switter, who was behind all this and made it possible. So thank you. Have a nice weekend, all of you. And let's hope for another occasion soon of discussion all together. Thank you so much.